Jacky already gave a very nice colloquium yesterday. So, for those of you who weren't there yesterday, he summarized very well various concepts of effective field theories and scales, why we need effective field theories. To repeat for the audience who weren't there yesterday, Jacky did his PhD from GIFR. He did his first PhD postdoc from Montreal University, then he went to TUM in Germany, and now he's in Los Alamos. Today, he'll be talking about recent developments in effective field theories and their various applications. Over to you, Jack.
Thank you very much. So, before we get into the today's talk, I will be brief overview what we discussed yesterday. So, both talks are kind of connected. So, yesterday, basically, we motivated that why effective theories can be useful in the present situation, given the data from the large language provider. So, we motivated that effective theories can be used to create to prioritize in such a situation. So basically, what is happening is that from LSC we haven't seen any new particles. So it looks like that the scale of new physics is much above of the electric scale. So it looks like it's much separated from the electric scale. So in that case, whenever the scale separation, one can construct like a physics theory. So one can construct the EFTs between electric scale and a scale of new physics and use that to study the new. So this is very similar to what to the situation for the standard model when so there basically there was a scale separation between electric scale and the lunar scale of quark space. There we also used so-called weak effective theory in a very similar fashion. So so in the today's talk I will be mainly focusing on the important concepts in the EFTs and I will talk about the recent developments that took place in the last decade. So interestingly, even though these EFTs are known for many years, like standard EFT was proposed in 1986, but the major developments were only took place in the last decade. So this is the plan of talk. We will start with the basic principles in the effective field theories. Then I will introduce to you three effective field theories. Which can be used for the new physics, which is standard model EFT effective theory and neutrino standard model EFT. This is just a neutrino version of standard model EFT. So interestingly, this weak effective theory, as I said, it was used for standard model, but even there the completion of its anomalous dimensions or very important calculations were done only in 2018. So I will present those developments. So I will discuss mainly three important concepts in the EFTs. So first of all, EFTs, normalization scheme dependence in the EFTs and power corrections. In the second part of talk, I will discuss the application of all these concepts for the particle physics, the flavor physics, or other observables which are important. In the particle physics. Okay, so we start with the principles. So in the particle physics, whenever we have heavy particles, basically we can integrate out those particles. So let's say at scale lambda, we have particles of which has mass of the order of lambda. So one can integrate out these particles and construct the effective field theory. So as a result of integrating out these particles, this result into basically the addition of many higher dimension operators in the Lagrangian. So when you integrate out the particles, so this results into the addition of these operators. So that is what we call an effective field theory. Say that we have some full theory. So we can take some example of standard model. Okay, in standard model, let's say there are heavy particles like W electrons. Integrating out them out will give us this effective field theory. This will be QED plus QCD plus the series of higher dimension operators. Often we, depending on the energy regime, we will need a letter of EFT. So one EFT is not enough. For instance, we are working, let's say, at scale lambda. So we will integrate out all the particles which are which has mass of the order of lambda, and construct, let's say, effective enthalpy 2. Okay, so this works between m and lambda, and so m is the, let's say, lightest particle, heaviest particle in this case, EFT2. So then, if we want to work with variables which are relevant below m, then we have to construct another category by integrating out all the particles which have mass m. So similarly, we have to and this procedure goes okay. So this is with the logistics. Why do you need high dimension? So this is the result of integrating of the heavier fields. So say that we have dimension for the gradient. Okay, that's a psi or psi, psi or gamma psi being some interaction of z on this one. So if you integrate out z on, this will automatically result into addition of psi dimension. So basically, the information of this theory that tiny small Lagrangian that talk about will be transferred to the coefficients of the dimension. Related to? Yeah, so when we integrate out a particle or remove a particle from the heavy particle, that's how we integrate out lambda from the theory. This will result into a series of higher dimensional vectors ranging from 4, 6, 5, 6 up to infinite. Okay. But depending on our need, we can truncate the series. We will not work with the full series. This is that right, infinite comes in the dimension. But we will always truncate our series depending on our needs, on the basis of experimental information that we have. So when you take the range of the mass, particularly no, this has a range of the mass nothing to do with the dimension. I mean, it depends. Of course, it depends. So because okay, we will see that the higher dimensional vectors are suppressed by mass. Okay, this is second scale. So as you go higher and higher, the mass dimension of operators they are more and more suppressed. So depending on m, it's possible that you might have to truncate at dimension 6 level or at 8 level, depending on the value time. In that sense, it matters. The value time matters. I hope this is clear. This is your question.
At the scale capital M, the field modes can be anything, like arbitrarily now. The field modes, see, when you say you are integrating particles above some scale M, that means you are integrating out the fields. That means their momentum and energy, everything, right?
So here, basically, yes, integrating out the.
But whatever leftover fields, they can have very large momentum, right?
Exactly.
And when they, undergo scattering, don't you expect those lambda particles that you?
No, so okay. So I think that this is a very important part. I should have mentioned it. So say that we are studying some scattering in terms of only light particles are left. Let's say L means light particle, and we have integrated out the heavy particles. Okay, and the scattering is in the light particles. So basically, you're saying that so this is a dimension 6 operator. Let's say. So when you want to study processes in which m is high, then you should not. If m is comparable to p, then you should not use the effective because so lambda is our limit of the validity of our. So after, if you want to study those processes, you should not use it.
Okay, so when I am at this scale capital M, I have to care what to study.
If you are at scale M and you're studying processes in which transfer at that scale, you have to be very careful because even higher dimension terms could become important. Even though higher dimension terms are suppressed by M, but this momentum that can there can be compensation. So I would not use. I would use EFT when the scale of my phenomena are much lower than M. Only that.
It's similar to this effective potential calculation where you integrate out hard modes and soft modes only remain.
So at the threshold.
A clarifying question, is that possible to ask now?
Yeah. Please ask.
Yeah, just in the previous slide. So what you are saying, most of it I cannot hear, but that's okay, and that's part of my problem. I'm joining online, but just wanted to clarify very quickly. So you mean that an energy scale is very high, the actual theory is a local theory, and when we integrate out stuff and get an effective field theory at a lower energy, that's a non-local theory?
Yes. So
Is,
you start. We can start with the local theory and integrating out stuff will give us the local interactions. But so that's a transition between the full theory and effective field theory. But you can also match the two effective field theories. You know, if you have one EFT and you hit a threshold in there within that EFT, so you might have to construct another EFT. So this could be transition between full theory and EFT or EFT to EFT. Both cases are possible if you see my slides. So first case is we can match full theory to EFT, and second case is matching between the EFTs, two EFTs.
Sorry, where are these two EFTs coming from? Because you are integrating out stuff in different ways.
Yes. So actually, so in this EFT2, the heaviest particle is of mass capital M. Okay. And when we hit this threshold, when we want to study processes much lower than mass M, there we integrate out this particle M and construct it in
Right. Okay. So where do you see non-locality? Where do you expect to see non-locality?
So non-locality will start itself from when you match your full theory. Let's say it has only dimension 4 interactions. Okay, only renormalizable interactions. So there itself, if you integrate out particles, you will see non-local interactions. But you can, I mean, in quantum field theory, you can also call this dimension 4 interactions as a local interactions, right? They are also at same x space-time point. So you can also call them local. But here, local means you generate higher dimensional local operators. So say that there's a 4 fermion operator, for instance. That kind
right. So if you integrate out some field of mass, say M, then there is a corresponding length scale involved. Would you not expect the effective theory to become non-local at that length scale?
So actually, at the tree level, we are writing the interactions at the same point, okay, at the space time.
Right.
But that eventually breaks down, and you have to do the renormalization. So that basically fixes the problem.
Right. So in effective field theory, you are supposed to write, tree level diagrams, but the vertices should be understood as some blobs which have contracted to a point because you have integrated out some fields, and the size of the blob will be related to the masses of the fields that you have integrated out. I think this can be argued using perturbative theory.
Yeah, in principle, this EFT at the tree level that we interaction right, this doesn't work. I mean, once you not do even in the normal theory, okay, ordinary theory without higher dimension operators, these theories, also need to be fixed, renormalized. So see, in the same sense, we also need to renormalize effective theories.
Yeah, I'll let you proceed. Thank you so much.
Okay. Yeah. So here, this is basically the very similar slide. So I was just saying that at the threshold, we impose the condition that the two theories should reproduce the same theory. Okay. So we might have several thresholds depending on the EFT that we are using. So at the threshold, we impose some relation between theories, and that process is called matching. And since as I already mentioned while discussing this question, these EFTs are also quantum field theories. We have to normalize them, and as a result of this normalization, the parameters of this theory those are also called Wilson coefficients. They become scale dependent quantities, and they involve basically the energy scale. So, and this is given by this evolution is given by normalization group. So we will discuss those things in detail in the slides. Okay, so So we start with the dimension for Lagrangian after integrating out EFTs. So this will result in addition of all that. So the good thing is that we always have finite number of parameters in that dimension. So otherwise, practically, it would be impossible to do this. And so these terms L5 and L6, the terms in this, the operators in this part are suppressed by power of lambda. Okay, as you go higher and higher in dimension, so they are suppressed by power of lambda. Sorry? No, to begin with, actually, we can say that let's say dimension 5 is suppressed by lambda, dimension 6 is suppressed by lambda square. Okay. So this is a let's say dimension 4 Lagrangian. So higher and higher suppressed. So to begin with, I'm just calling it as lambda, but in principle, this lambda would be different for different operators. So basically, you fix these parameters of this theory, the theory C5 and C6 from experiment, and depending on the your observable lambda could turn out to be very different. It could be sometimes it's order different by order of magnitude.
No, but in the philosophy of EFT, you have a single lambda, right? Presumably, when you integrate it out in one scale, you generated one scale in the denominator for all of them. The uncertainty is perhaps encoded in the C, right? C could be different for different processes. But in the philosophy, you agree that it's the same lambda for all of them.
So it
Usually you don't introduce different lambdas for different objects, right?
yes. So we can
Say lambda over C, you will call it a new lambda.
Yes.
That's just an interpretation. Right?
Yeah, that is the interpretation. So usually in my talk, and I will be using this C over. I will be defining basically C prime, which is C over lambda, C prime and C6. So, but you're right that yes, if we stick to one lambda, we fix that eventually, then different experiments will give us different values of C. Then we interpret the value of C.
I think what you had in mind was from very high energy experiments, we get a cutoff or a bound on lambda of the order of few tens of PeV at most, but from some flavor physics sector, it can go to some hundreds of PeV. So that interpretation probably we're trying to extend, right?
Yeah.
But like,
Yeah, so
this point is.
yeah, in that case, we usually assume that C is things.
Yeah, so, but like, in philosophy, there is.
Yeah, but then you say that that is the result of integrating of different physics at different states.
Yeah.
And then it gave you different lambdas.
Yeah.
But when you integrate out once, you take all the higher dimension operators with that lambda, with that scale.
Yes.
There are different physics being integrated.
Technically, since we define our EFT with respect to lambda, we can fix the lambda and fit the values of C, but we can reinterpret them later, in terms of lambda.
Because the model independence actually goes away when we start assuming any value for C. So until C by lambda to the power n is what our model independence lies. After that, any kind of interpretation has some kind of model dependence.
Okay, so using this Lagrangian with dimension 4 Lagrangian and then plus C in the 5 dimensional operators, so one can study the phenomenological processes. So the basic, if we want to give precise definition of EFT, which is given by Jacky, so I just copied it here. So 3 points are here very important. So using this EFT Lagrangian, you can describe the physics and even scale in terms of finite number of current. So finite number of current is very important. So when so this is very important. Otherwise, it will not work. In terms of finite parameter, with the desired accuracy, and depending on your accuracy, you can truncate your CD. So So when I write this Lagrangian in full generality, there are finite number of parameters. Even with the full generality, there are 4 is finite, and 5 is number of parameters are finite. The finite number is very large. It could be very yes. 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 So we often that number or no, so here I'm talking with full generality, okay? So here I'm basically I want to convey the message of validity of effective systems. So once let's say the parameters are not finite, okay, what would happen? Irrespective of reducing them or challenges that we face, numerology, fitting in, etc. If the parameters were not finite, the theory is not normalizing, right? So then you need infinite number of proper terms to normalize the theory. So only with the transition it works.
But by definition, this C have lower dimension because we are saying this O operator will be O5 will be 5 dimension. The coefficient will be of that one
Coefficient is dimensionless because we have suppressed it by power. So we have compensated the dimensions of operator by lambda. Okay, so everything is dimension 4. The C's are
5 dash 5 times.
yes, 5s are now dimension. They have dimensions of respective terms.
They will be not value. Yeah, that's vacuum dimension.
Yeah, technically, I mean, with the negative dimensions, the theories are not normalizable. But if you stick to if you truncate your series, they are normalizable. In fact, we will normalize it. We will see the explicit normalization of this series, which is one of the development that took place in this last 10 years. So they can be normalized if you truncate them.
You mean higher and higher loops don't generate new operators?
No. So
Because from symmetry or what? In general, it should, right? It should in principle be non-renormalized. You cannot absorb it in the finite number.
no, so if you
Even order, it will be finite number of operators.
yeah.
But if you keep going to any order, then it should in principle be non-renormalized. When you
If you keep on adding orders, then yes. But
Yes, yeah. If you say that
fixed order it is, but otherwise it is
non-normalized. Yeah. That's so technically I said in with full generality this is non-normalizable theory. Okay, but you can normalize it if you truncate it. So even when you normalize your theory of truncation, you have to track the power of lambda. Okay, you should not ever exceed the power of lambda. So using the power function. Once you do that, you are in trouble.
Yeah, with that principle, it becomes a predictive.
That principle is
Sorry, regarding this comment about non-renormalizability, the theory may be non-renormalizable, but it can be renormalized. I mean, counter-term renormalization process goes through. I think in the context of effective field theory, that's what matters. Because all the interactions that exist, they are non-renormalizable in nature.
yes.
There is no good reason to believe that we have a renormalizable theory. We have a non-renormalizable theory. We are observing things at a particular scale, which is why we are seeing it to be renormalizable. But when we take higher order corrections, higher dimensional corrections, those are non-renormalizable interactions. But
Yes.
we can still you can still perform counter-term renormalization as a process. I think that's what you mean when you refer to renormalization in this context, right?
Yeah, I completely agree. You can normalize if you truncate
Yeah.
you can normalize. EFTs are normalizable if you truncate the series.
Yeah. Okay. Fine. Thanks.
So so we will discuss the first of all. We'll start with discussing effectivity with the tree level. So what the real power of EFTs we will see only at the when you work with okay. At the tree level this is just an expansion. We also saw yesterday. So suppose that we are studying this process which has some IR scales which are smaller masses and heavier UV scale, a heavier mass. Here you can just expand this amplitude in the powers of P over W square, P square over W square, and the first term is the leading term, and this all other terms they are suppressed by the W mask. So depending on your position, you can just truncate your series. So at the tree level, this is just an expansion. You can just expand it and keep your terms there you want. Okay. So here, I mean, there is no difference. You could also use the full theory. You could just work with that. There's no need of constructing the activity. So real power you will see at the loop level where you really see that you need to you have some advantages on using the full theory. So in this case, so this is basically standard model interactions. Okay, these are dimension for standard model interactions, and so this gives us this performing operator is some coefficient. Okay, these are predicted by standard model for these terms, and so if we can give this just some generic name GF or C, so in standard models this comes out to be this value. This is just in terms of this weak coupling and so that's basically the matching that I talked about. The one example of matching, tree level matching. So in the here in the full theory in this case was standard model which has these local non-local interactions or non-local interactions, and then in the EFT we had this local interactions and plus QCD plus QED, because we have integrated out W and Z bosons here. So we are left with only QCD and QED interactions plus a series of higher dimensional operators, which is as a result of integrating out the heavy fields. By the way, I think there was some question before that. How do you guess this higher dimensional operator? Here you specifically see that when you expand this in the powers of P1 and W square, you get a higher dimensional power. Yeah, so P will become basically the derivatives, and MW is over lambda in case of time. Okay, so here I will just mention the complexity that will happen at the loop level. I will talk about it in a bit. So at the loop level, the EFTs are they are much more rich and complicated. So first of all, you have to normalize the EFTs, and while normalization, you have to choose a proper scheme for the normalization. So we will see what I mean by normalization scheme, and choosing a bad scheme can result into various kind of problems. So we will see that all that. Okay, so before going into this technical stuff, I will just give very brief definition of these three EFTs, which I call modern EFTs. Although they're 50-year-old, very old. I'm calling them modern because recently, last 10 years, most of the development took place in the last 10 years. So first is this weak effective field theory. So this is just obtained by integrating out W, Z, and Higgs and top quark from the standard model. Okay, so you're left with only the light fields, which are quarks, leptons, photons, and we have this symmetry, resonance symmetry is the low W. So by imposing this symmetry and combining all these fields in all possible ways, we can construct the weak effective field. So this is QCD plus QED plus a series of higher dimensional operators. You can have psi 4 terms and 4 terms, terms like the psi square, FPC strength. So we have various kind of terms. So this
can I just wanted to have a quick clarification from the previous slide. When you said loop diagrams, since EFT is supposed to always come with a cutoff, so these loop diagrams will be cut off as well. So is it a finite renormalization?
So actually, I will in the coming slides I will argue that this cutoff is not cutoff creates a problem. If you use the cutoff, then EFTs are hard to deal. But I will talk about the finite renormalization as well as the finite parts as well as the poles.
Okay, fine. Thanks.
So this weak effective theory, so this is a review written in 1995. So that means various tests happened before that. So that's a review of all the development. So this is a very old EFT, but you see the complete renormalization was done only in 2018. Okay, so what happens is that before in the old times, people will take processes, different processes, and will do the renormalization process by process. Okay, so in the bits and pieces, this was done wherever it was useful, but the complete thing was only done in 20 at one time.
So there is
At dimension 6 level.
the full operator set, that whatever that.
For the pool.
1099.
Yes, that was 31 something else. Yeah, 31 something. 33,000 plus for the big 33. No, actually, when you do the loop calculation, you don't have to do that kind of hard work. You know, you can always treat with them. There are indices, right? So you can just treat like IJ.
Yeah, they were indices.
Yeah, and yeah, you can put it later, and actually, it's simpler than that. But they did the full thing at one loop level. So at this level, so before the renormalization has been done up to 4 loop level for certain loop. But complete thing is not at 1 loop level.
So this assumes the input at the width scale, at the W mass scale, that and runs it down.
Yes. So this is basically from MW to load.
And the full operator mixing everything for all the 3,000 things.
For the full,
are- okay.
Yeah. They just completed it. They just completed the gap.
Is it done in a like sector by sector? You know, some operators might mix on the renormalization running and some may not.
Yes.
And so is it usually done sector by sector, you know, whichever are that mix? Is it possible to in theory tell which are the operators that mix with each other and then into separate sectors kind of?
This is a little harder. They have divided the full set of operators into classes. Like left, right.
Okay. But how about which operators mix with which other operators? Is
That,
in theory decided?
That's a difficult question, and that's their contribution is. So they
They have done it,
have to think it what could mix with what, and think about all the diagrams
and they have done it.
they're done.
And they have segregated it into sectors
Yes,
where the sectors don't talk to each other, but only talk within.
yes. So
So
you
that's in theory decidable, that's without input from any physics. Oh, here it is a standard.
no. So within these practical theory, you can without knowledge of these things. So EFT.
Sorry, yeah, here it is different, so I was going to ask, so in this case, since the standard model is the completion, we can decide because we know the unit completion.
But that information is not needed to normalize the practical theory. This is a complete theory in itself, right? So you can do it within.
So we have to talk about the
Right?
good parameters.
I will.
What will be the input parameters for the code?
No, I will not talk. In this talk, I don't have, I think, but we can talk after.
Sorry, I didn't understand. Fixing of
So basically, when you do the renormalization, so a priori, you know, here when you start with this Lagrangian L4, L5, L6, so there are many terms, okay, and these are independent terms, okay, each has its own position. But when you do the renormalization, you calculate certain loops. So say that you are calculating a loop. So what happens is that one operator, insertion of one operator, can generate the other operator. So that's what I mean when we
On the theory, this coupling that you had in, we have mixing for all other.
in principle, yes, but
In the 4 dimension, there is no problem.
yes.
They have a higher dimension. The 4 dimension is not, unless you know that there is a relevant coupling. It will not have much contribution to the equivalent document. But if you have already equivalent document, you will have contribution to all other equivalent documents.
In principle from all, but once you do the normalization, you will see that there are some blocks which are independent. After the calculation, you can see that there are some blocks.
That comes from the symmetry or how do you?
So I guess that was my question. Like, if really can you decide which are the sectors that we need to take up? Because if we want to apply it to that case for usage, we would like to know that, right?
Yeah.
Because we don't know
So
what
you
is
can-
the
you can have
usage.
some-
If really we can decide which are the blocks that mix.
Yeah,
Really, really.
I think you can have some intuition based on the symmetry. Uh, Based on the symmetry, for instance, QCD doesn't violate the flavor. So the mixing and the QCD, those operators with different flavor will not mix under QCD. For example, same for QD. So, but I think for the full basis, I think one has to sit and think. Yes. So you
Yeah,
have
that's
to-
a good example. Yeah. So PCB and QD, like, there are different flavors.
flavor mixing will happen. So that will be also one of my very key point in when I discuss the phenomenology. So for standard model EFT, which is written above the letter, closer with power. So normalization group running gives you the flavor mixing as well, which is very different from flavor mixing doesn't happen at least running. It's only PCB and QD. That's due to that the phenomenology is very.
But the complication there is that at the matching scale, there are flavor of diagonal operators that we are using now, which is there in the standard code, right? And even in the weak effective PCB, you don't start with a flavor diagonal. You already have flavor. So that messes up this.
Yes.
Decoupling, right?
No, so if I have a flavor violating operator at the high scale, if I have it, QCD will not cause its mixing with some other flavor.
So
Some
we
other
have
operator,
already written down a flavor of diagonal operators.
yes, so we can take some examples.
So it will involve flavor of diagonal and diagonal operators, everything, right?
Yes. So what I mean by this example is this. So let's say you have 1, 2, let's say 1, 2 flavors, okay? So if I do QCD, that will not give me 1, 1, 1, 1. Even if I have written it at the high scale. But if ours can give it. So that kind of transitions will happen in the standard model.
Sure.
In standard model, you have this flavor changing equal currents of a process. So even the flavor changing equal currents, you show that something flavor changing.
So they are driven by CKM itself. So these transitions in the normalization group running is not driven by CKM. Because we have all the fields of standard model and all the interactions for standard model, nothing beyond that. So it's driven by all the standard model interactions. So flavor transitions are flavor. This flavor mixing of due to product mixing is proportional to CKM.
This is always
It's
even in this at least in this sector we do not have much flavor.
no, so those transitions, those are also important. Even though this happens through CKM, those turn out to be very good.
Even in equal currents.
Yes. Those but basically CKM is a charge current, right? It's a charge current network. So I have one example. Postpone to the. So this is we have already talked about each theory. Then for standard model EFT, so here we are writing theory above the electric scale. So there is symmetry, full symmetry, and the fields the spark doublets, left doublets, various other stuff. So here we basically follow the same principle and write down all possible interactions. And this was already done in 1986 for Kumar and Euler. Then this guy is found that some of the operators are redundant, and then final basis is known by the person basis. So this normalization, I think, was started in 2013 by San Diego group. It was done in I think 3 years. Okay, then comes the so the standard model EFT has something very important missing, which which is a subjective statement. So it includes only the standard model fields, but you know the right-hand neutrino, which is not part of standard model, is very well motivated from neutrino phenomenology. So this EFT, if you stand the standard model EFT when neutrino, then we have a bunch of more operators. So this is known by the name of Newsmap. So if you want to study neutrino phenomenology, then you have to include it. So so the complete basis was given. I think I could not find the exact paper for this. I think the best I could do is only this paper by Budka and company in 2008. So they gave a I think pretty complete basis for that. And normalization was proposed from in the form of two papers.
So is it that you take the old operators and then attach a new in some places? Is that how it is done?
No, so it's for instance, so you can have something like this. So Q and bar. So this is a new
Yeah,
operator.
that's what I call attaching.
Okay.
Oh, yeah, so you can take
Yeah.
pieces of it. You either attach to the standard model operator and generate higher dimension operator.
Yes.
Or you replace some other field in the old without the new with the new, right?
That you can do it.
Is that how they generated it?
I think this is pretty simple here. I would
Yeah.
say you can do it. You can do it. Yeah, in 1 hour if you sit down and except few operators are complicated, but that's why there's no name for this or like
Okay.
what services is done. Pretty simple. And renormalization that we did is also simple to use map. And a lot of information you can take it from map itself. You know, but that is always true. Even for Snap, so they took a lot of information from web. This is true. Okay, so I will give you a very brief overview of renormalization. So first of all, like in this example, when we integrated on a W boson, so now we are turning to EFT at the loop level. So we take the same process, it's like for mediated by W boson, but attach a glue. So now it's a loop. So similarly, we will do it on the EFT side. So here, you know, the things become more complicated. First of all, you know, standard model is a normal, you have already normalized it. So all that stuff that you calculate in standard model will be perfectly fine. It will be fine. You don't have to do anything. But in EFT, once you calculate the loop, so you have to renormalize it again. So there is no one-to-one correspondence between divergence structure of this EFT and the full theory. So meaning once you construct your EFT from a given EFT or a full theory, you have to normalize it again. Okay. So these operators, these effective operators have their own divergence, which are additional to full theory. That basically gives the normalization good value of
So that's because the integrals that appear here, there is one extra propagator, right? So the integrals that appear are different kinds, is that or different? Really, because
No, I mean,
extra
so,
propagator.
no, I mean these are simply new interactions. So this is a new theory which has a new interactions.
No, but everything is the same, but for one propagator, right? So there is a W propagator here or whatever the weekly line. Only that is extra. That is replaced by a contact link.
Yeah.
So in the integral, all I have is one extra propagator. Right?
No, so
The structure is very similar.
yeah, so another difference is, for instance, the insertion here, this is a dimension 4 vertex,
Right.
dimension 4 copy. But this vertex is a new vertex.
But the kinematic, the loop kinematic does not see all that, right? It's just that I put a loop momentum. It's one loop here, it's one loop there.
No, loop will see that, right? So loop will certainly see that because let's say you are inserting this operator, okay? So if you start calculating that, so this is a fermion propagator. Here you have gamma mu, let's say.
Everything. There is the same fermion propagator here also. There is a fermion propagator. Only thing different is one extra that gauge goes on propagator. That's the
Yeah.
only extra.
So that is replaced by a new Dirac structure here. Right?
New Dirac structure.
Yes.
the numerator.
Yes,
So the denominator will get one extra propagator and the numerator structure.
yes.
But no correspondence seems to be too strong a statement. Still, many things are similar. And they should go to each other in some.
So what I mean by no correspondence is that there are additional levels in this, in the, yeah. So apart from, let's say you take standard model and normalize it, all the companies, all the terms, okay? When you go to big factors, there will be additional levels, which you have to perform the computer again.
So if I look at the coefficient of the pole here and the coefficient of the pole there.
Yeah.
There is no similarity.
So some of them, some poles will be cancelled. So you will see. So this is an example worked out very well in Kumar. Okay. So there he shows that you have some divergences here, okay, and some divergences here.
Right.
Some of them are similar. You can cancel them.
There will be some similarities, but some different.
Yeah. So
So
after
the coefficient of the pole, there will be some difference. So that's your point, I guess.
yes.
So
Some-
you have to recompute.
Some of them will be cancelled, but then there will be some remnant divergences that you have to.
So I suppose your point is if you have a calculation of this, you cannot blindly use it. So you have to recompute. Is that the point?
You have to recompute.
Yeah.
So I have to comment that for the inductive connection, you are not completing the current diagram for the.
Sorry?
Yeah, you are shown the DC connection. This is the inductive connection. So basically, that the frequency of the you have less number of quantifiers.
So in this, this is a big factor. The W is not there.
Yes, and
No, but these are all dimensions of it. In element of. There may be more other contributions.
No, his point is, if it is a full theory, here, instead of attaching the glue on, you would have done a one loop correction of the gauge question, right? But he's talking about QCD correction. That would not be that would be an electro, right? So, but yeah. But he's focusing on QCD.
Yeah, so I'm just introducing bit by bit. Then you will see electrical correction here. Some examples. We can discuss there. So
Sorry,
the first-
I was asking this question earlier. It is, I think, relevant on this diagram. On the right-hand side, in the loop, in right-hand side diagram, in the loop, are you supposed to allow the loop momentum all the way to infinity?
in principle, yes. So I will
No.
talk about in the coming slides about denomination scheme where I will use dim rag versus. I will talk about dim rag versus cutoff. So there you will see that you will calculate the full loop, yes, allowing go up to infinity.
Sorry, I didn't follow the last statement that you made.
So yes, I will include the all the full momentum.
Full?
Yes. I will integrate it.
No,
all.
you will allow the momentum to be arbitrarily large, right, on the straight lines.
Yes. So
Why is that so?
Not on the external lines, on the internal lines. I mean, when you compute the
No,
loop,
those lines which are the straight ones, there are curly ones, and then the gluons, and then fermions. So
Yeah.
you will allow the arbitrarily large momentum to flow in that line. Now, I'm asking, how is that consistent with integrating out this that composite vertex that we have drawn? And if you allow arbitrarily large momentum, then it will see the internal structure of the vertex, which is basically equivalent to saying that the effective theory is supposed to come with a cutoff. I'm not following. There must be some argument which I'm not
actually,
following.
we were discussing this point with Siri yesterday. So you can actually we will okay. So when we work with dimensional evaluation, so basically we redefine your parameters. So we redefine our effective theory. We can redefine our EFT parameters and fit them from the experiment. So all those that information I think goes we dump into the finite number of coefficients of the EFT. But
So is it if let me try to rephrase what I try to ask. Suppose this the gluon propagator, you remove all the gluons, and the particles that you are integrating out, you take only the subsector of the theory where those particles appear, where those lines are present, using. Hello.
Yeah, please continue.
And then you take that subsector of the theory, of the full theory, where all possible lines appear, which you are going to integrate out in the effective theory. So that is where all the possible places where those lines can appear. Now, this is again in the framework of perturbative QFT, and you can calculate the effective action for the fermions out of this. And in that effective action, you have all possible tree-level fermion vertices. Even if the fundamental theory say have a 3 vertex, but if you integrate out all these internal propagators, which you are integrating out, then you will end up getting a theory of fermions, but with all possible 3 vertices. And those vertex factors have the information about these interactions that you are integrating out. And those vertex factors have to be denormalized, and in dimensional regularization, they will flow with mu. And then if you add this gluon propagator in that effective theory, then you will have a diagram like right-hand side that you have in the right-hand side. And then if you do again renormalization, then there is another mu that is coming in. These two mu are not independent. And you will have to, if you write now if you get a 4-point fermion vertex out of the right-hand side diagram, that vertex will run, but that running will be coupled to the running of the box that you have drawn in the 4 fermion interaction. That coupling will also run with the same mu. So it's a mixed up system. That's what I would think. So maybe I should wait until you tell me the entire process, that what exactly you are doing.
Yes, okay. Yeah. So if something is left, maybe we can talk afterwards in detail if possible.
Okay, fine.
Yeah, here I will just sketch out the basic procedure of normalization. So we will do it like we do it for ordinary theories. So you have this Lagrangian with one term, let's say. So this is the coupling and the operator. So their operator and their coupling, which is noted by the zeros on the top. So this could be, for instance, dimension 6 operator as an example. Okay, you can have other operators. So the normalized version of the Lagrangian will look like this. So there you will see C's will become scale dependent quantities as a result of the normalization. So these are just the definitions of bare Lagrangian and normalized Lagrangian. So basically then, so this is how it is done. So you compute all kind of these QCD corrections to this. For instance, if you normalization with respect to QCD. So these diagrams will turn out to be divergent. And so then you can redefine your operator and absorb all the divergences. Some constant, they call the normalization constants. So that basically gives you a normalized one. So basically, you compute all these divergences here and cancel using some and absorb them all of them. So we can reinterpret it in terms of the parameters of theory instead of operators. So here you can define your normalized coupling as C times. So now, since the bare parameters are scale, that comes from the 3-level Lagrangian. Those are scale independent quantities. So if you differentiate this equation by log mu, you will get this equation. This kind of equation where gamma is given by basically this quantity. It's given by basically normalization functions.
Sorry, D is usually some wave function. Or are you using the term generally?
No, so that's the leftover thing. So this is what we discussed here. So this is the leftover divergence of the operator. So those are those poles are in the Only,
You have done wave function renormalization and that's all done with it, and you're focusing on something that's left over.
yeah. That's
So-
within the EFT.
So the Z factors are what is there in the full theory itself, the same thing, I suppose. Or are they also different or what?
No,
I'm a
so,
bit confused. So when you say Z, does it include wave function renormalization and vortex corrections or only one of them or which one?
it will include wave function and vertex.
Okay,
So vertex means this new vertex is there,
right.
only the new vertex.
Yeah, only the new vertices are there.
But it happens that this, so you have to consistently to do it.
The vertex counter terms also you're calling as Z. So you usually add counter terms, one for the waveform and one for the vertex. Right? So are you using a common terminology?
Yeah, this is very rough.
For both wave function and vertex.
Yes, yeah, I'm using it very rough, yes.
Oh,
So the wave function, you have to do it and combine it properly.
right.
So there's a formula for that. And some of the vertices are cancelled by wave function.
Okay.
Then you're left over.
That's right.
It is more.
And then you add vertex counter terms also.
Yes.
But you're using the same Z notation.
Yeah,
for
this is
the
very,
next-
very sketchy, yes.
I see.
You have to, there's a.
No, as long as you tell me that it is that, then it's fine.
Yes, it's there, these vertex corrections, sorry, the wave function corrections are, you have to take into account.
But you are not focusing on it. You are only focusing on vertex correction.
Yeah, for the moment, yes.
So for the starting product, you want to know that like the character is not denominated by the system. Okay. So then you see the benefits.
I mean, depending upon the fields that we are taking, let's say, marks. So we will see that which part we want to use. So if these are all left on there, so then gluons will not contribute. So it depends on the field, right? So which fields are there in the operator. So if you, for instance, take this fully left on operator, 4 left on operator. So there you cannot attach the gluons. So then it will not depend on the gluons. Even for the quarks, it will depend on the gluons. Because there, if it's quark, then you can connect 2 quarks by gluons.
Sorry, what's the question? So here in this diagram, that would be box connected by a Z. That's an electronic.
Yeah, you only need
But there would be a vertex correct mouse.
but you will not need to.
No, electronic.
No, electrical couple is not there in the. Here.
Yeah, because
Also-
he's focusing on physical.
Yes.
So that I suppose we have already done that. So if you take a normalization like kind of model, you normalize it. If you are constructing an EFT out of using the standard model by integrating of some field, so you will use the normalized property. They're like alpha X or all other companies you will use. They're already normalized, right? You don't have to do the again. But it can happen that these new operators can contribute to their running. It can happen. This happens in fact, yes. So these new operators can cause the running of additional can.
Check inside the document.
Okay, I think I have a lot of stuff left. So I will go really, really fast then. So normalization. So we just performed the normalization of this new SMAP. So this is very similar. So technology we have already discussed. So here we compute all of this.
So-
Right? Yes.
Sorry, probably the last question. I know I'm stopping you again and again.
No,
The renormalization you just described, I think there's a coupling you denoted by G. that is that box vertex?
No, the Z is a renovation constant.
No,
So
no.
I thought the
G. The coupling, G.
so I'm going to
The small G.
yes, small g is if you can refer to the slide, small g is yes the QCD
The
coupling.
effective coupling.
Yeah.
Is that the effective coupling?
No, the Z is here the this QCD coupling.
The no, that's a renormalization, right? I'm saying the boxed in the previous slide you showed that picture on the right hand side. The box, yeah, this boxed effective coupling.
This is C.
What is that coupling in your later slides?
It's C. C not
Okay, C. And you have a running for C?
yes. C
Where
runs.
is that equation? C must run.
Yeah, so this is the equation.
Yeah,
for,
this is C. Yeah, okay, fine, C. But this C, this effective coupling must also run because of the renormalization of the couplings that you have integrated out. But you are not taking that effect here because those are at higher energy. Some adiabatic approximation is going on.
Yeah, so actually I'm working with the let's say a theory which has let's say QCD interactions plus higher dimension operators. Okay? So only those interactions will play a role within this EFT, right? Because this is in itself is a well-defined EFT. Without referring to what I integrated out, I can work with this EFT, right?
No, but actually in the full theory, what you have integrated out is also running with the scale.
But
and that is not
for the renormalization of this EFT weak effective field theory in this case, I don't have to refer to that. So
why in the full theory? Suppose you embed this calculation in the full theory.
Okay.
If you embed this calculation in the full theory, everything is running. So you are ignoring that running because you think those are fast variables and you are taking an adiabatic approximation. You are treating them as classically fixed things, but they should also run.
Actually, I'm doing the things by steps. So that part will be taken care of by the matching at the matching scale, right? So at the matching scale, all that information will be imparted to my EFT from the full theory through the process of matching.
So okay, not allowing the loop momentum in the effective theory to go to infinity and do the infinite renormalization, is this a mathematically preferable thing to do? Because physically speaking, there must be a cutoff, because there are certain fast variables at a higher scale which you are ignoring, and your theory does not know about that in the effective theory. So you should not allow momentum to go to infinity. But you are still doing it. You are still doing it. Maybe there is a mathematical advantage of that, which is what I'm trying to figure out.
I will talk about it.
Okay, I will wait. Okay, fine. Thank you.
Conversation we were having.
Yeah.
So I think what you just said about the matching, I think is the key. Right?
Yeah. So there we impose that the two theory should match.
Yeah.
Okay, maybe that's where the answer will come.
There is also mathematical advantage of using this not using cutoff. I will talk about it very quickly.
Yeah. Okay. Thank you.
Always take scale everything. The theory looks the same in every.
Yes. But I will not use this only. Here I'm using the dimensional evaluation plus MS bar. I will talk about that why this is better.
So in all this, the matching is because you match it at that scale.
Yeah.
So
Since I'm a Latin based student, I usually in RD. There actually the moment is
yeah, it should correspond to that because you match it.
But there's a little advantage of using DIMRAG in our set. Yeah.
That's a technical advantage.
Yeah.
It should be true to the physics of it, right?
Physics wise,
all the questions is about you do this technically,
yes.
But is it keeping the physics honest? All of these questions are the same thing.
Okay.
And so perhaps because of the matching, it is true to the physics.
Yeah.
And you have a technical advantage.
Right. Okay, so since because of the time, I cannot go to the details of this paper. So basically, it's the same technique. So we compute these diagrams and compute the running for these parameters of this. So various kind of diagrams.
Sorry, how many operators are involved there?
News what?
So in what, in the expression, you know?
There are I think 16 of them without flavor.
So all of those C and D, they are all Wilson points
Yes. Yes.
of some operators.
Yes. So without flavor, I
All
think
dimensions.
all dimensions.
And these are the ones that mix, right?
Yeah.
All the ones that are.
Yeah, you can see that ND can mix with NU, ND,
Yeah.
and so there you can now divide into the blocks. Yeah.
So how come there is no loop factor?
No, actually there is a, I'm omitting it, so there is a, so it's common in all the
So you have omitted that.
yeah. So actually this C dot is defined basically one 16 pi square D C over D. This is usually the convention is but
This is all one loop, right?
yes, one.
Okay. And sorry, the gamma, that matrix is the gamma matrix that you have on the top. So this coupled equation, that matrix is the gamma matrix.
This is the matrix given
Yeah.
by all the coefficients. Okay, so let's go very quickly over the normalization schemes. So some slides are repeated, I will skip them. Okay, so there are two kind of schemes basically that you can use. One is cutoff. So that while calculating loops you can put simply cutoff or use dimensional aberration. I will talk about it. So I will argue that in the cutoff, if you use the cutoff, there are problems. There are practical problems in using the cutoff here. So basically, what happens is that there are two kind of schemes basically. So like moment cutoff is a scheme which is a which falls into the class called mass dependent scheme, and there are mass independent schemes. So the difference is that when you compute the loops in these two schemes, so in the mass dependent scheme, the loops will produce the powers of some dimensional parameter. That will not happen in case of mass independent scheme. So that you will see one example here. So I will argue that MS bar minimal subtraction scheme is better than cutoff. So for instance, you are computing this. You take this for effect EFT vertex. You are computing this too. Okay. So we will do very naive dimensional analysis. So here this code
You took that operator and closed it. Is that?
Yes.
I missed the point.
I just closed it. Yes.
But you get a different operator.
Yes. I get a correction to Z coupling.
But Z is a heavy field. How can you attach Z?
No, so this I am doing at the matching scale. This is not a normalization. So this is not a calculation of normalized dimension. This is a calculation of matching.
So this is a calculation in the UV field.
At scale lambda.
In the UV field.
In the UV.
So all fields are propagating.
All fields are. It's in the standard model.
Whereas this one is the effective operator that is valid below the scale NASA.
No, so you can also write.
Now I'm a bit confused. So which is the effective theory operator, which is the full theory, and where are we doing this calculation? So is this, so clearly the left hand side is an effective
It's an
theory
effective.
below lambda, right?
Below. So okay. So this particular example is I am computing this correction to Z at scale lambda. At Z scale. Here Z is also there.
At scale,
Yes.
including loop momenta above lambda, or not?
Yes, we will as we.
So if I'm doing it in the UV field, I'm going to include loops and integrate over all momenta, right?
Yes.
And then I can do the same calculation in the effective field.
Yes.
Right, which is valid below the scale.
Yes.
And I can match it at this scale. Is that what you're referring to here? Or I'm like missing the context here. What?
No, this is just okay, so this is just a calculation of Z vertex, correction to Z vertex
Okay.
from the effective operator.
Which clearly then is valid below the scale lambda, because I can use the effective theory only below the scale.
Yes, but you can use it below the scale lambda, then you can integrate out Z. But yet we are not doing that. This is just an example.
Then I don't know what I'm. So here, what it's like the standard one. Z is still propagating below the scale lambda, right?
Z is not propagating. Okay, so
Are
it
we
depends.
doing weak effective field theory, or are we doing which one is it?
this is actually at scale Z.
Oh, this is weak effect.
Yeah, weak factor theory at scale Z. Because we have
Then Z should not be propagated because clearly I have integrated the count.
yeah, but at scale Z is present there, right?
No, I mean that is one point, right?
Yeah, so matching is done at that point, right?
But then I cannot compute anything using Z because Z I cannot put propagators. It's not a propagating field. It's just like an auxiliary field which can be integrated.
So you can think
Well,
of,
maybe you should proceed and we can
Okay.
talk later because I don't want to hold you.
so but yeah, so here the point is not okay. Think of this as some loop, okay? So some correction to so this could be let's say Smith order. It's coming from Ireland. Okay. You are computing the correction to the Z from Smith.
Yes.
Okay.
Then it is
That's
valid. Then
possible.
I can put the.
That's
that
possible.
there.
Okay.
Yeah, that is. fine.
That's just one example.
Right.
So when we compute this loop, so this is a dimension 6 vertex, that vertex, okay. That is now divided by 1 over lambda. So this goes have a d for k 1 over k square. So here this produces k square, dimension like k square. So if we set this k equal to lambda, which is a cutoff of theory, so then you will see that we produce all one. So in case of Jacky, this will be equal to lambda. Right? So this will give a okay. So my main point is that this loop diagram in cutoff is giving powers of lambda. That's my main point.
If you cut it off at lambda.
Yeah.
Okay.
So if you use cutoff, loop
Yeah.
diagram, loop produces power law in the lambda. That's the point. So then it becomes hard to track the powers of lambda, right? Because so you have dimension 6 for the whatever the range is. So you insert you want to keep track of the power of lambda, but if you start producing a power of lambda, then the power comes into down. So similarly, if you do it at dimension 8 level, so you will see that those are also those will also generate order 1 term.
But
So-
the gauge invariance is supposed to not give you such things, right? I mean,
Gauge invariance is also broken like it in the cutoff. That's another.
spontaneous.
That's other.
Spontaneously, there are still word identities which are exact.
Yeah. So that's a okay. So if keeping aside that.
It can happen only in the Higgs sector. So that doesn't have any protection. So you can get such things, which is the origin of the hierarchy problem. But otherwise, the what identities are intact. In the gauge sector, you should not be getting any of the order ones. Right? But we can talk about it.
Yeah. Okay. So if you compute the same loop in dimensional relation, so you will produce something like this. So this M is mass of this light field in the loop, and the logs. So this dependence on this scale for dimension full parameter is only inside the log. So you will not produce the power in the logs. That's the only dimension power of dimensional relation. So I mean. So all the powers of lambda will only appear from the vertices, okay? So if you insert dimension 6 vertex, so you can track very easily the power.
Yeah, this is a bit tricky because putting a 9 momentum cutoff breaks gauge invariance. So what I was referring to as the word identity being exact are being destroyed by the regularization scheme. So you will really see what you are playing because you've destroyed gauge invariance.
Yeah.
And so I guess another way of stating that is, MS bar keeps gauge invariance intact.
Yeah.
While nice fraction, and so you start getting more.
Yeah, usually people talk say in that term.
Yeah, I'm just rephrasing.
Yes.
Yeah, okay, that's how I.
Okay, so I don't really have time to discuss about that, but I will. So how much time more you can allow me?
5 more minutes.
Okay.
At first.
Okay.
Yeah,
The
you
sketch
want
work.
to tell
Okay. Okay, so basically,
for your complete
I will say it in words. Okay, so the scheme dependence basically comes from the finite parts. Okay, when you do the normalization, you cancel the contour to poles. Okay, of the divergent pieces. So then the question is, do you want to also subtract the finite parts and which finite parts? So that's basically scheme dependent. So when you're computing these loops, so there was scheme dependence coming. But your final result should be scheme independent. So you have to keep track of what is your choice, what choice you made for the final part. And final parts can in a loop can result from various things. When you solve the Dirac algebra, bunch of comma matrices places, so that can give you final part. Or there are different sources of final part that can happen in the loop. And all those that you have to track. So there are different sources of evaluation scheme dependence in the process of implementation. So here in this paper, we just in case of SMAP. So when you are doing matching of SMAP 2 onto web, so there we computed basically the extra matching corrections which are required to make sure that scheme independence is best. So this is basically that correction. And so in this case, as I said, the final part can result from various things.
Jacky, I'm sorry to interrupt so late when already you've been interrupted. I just want a clarification. So when you say scheme independence, see the operators and the coefficients themselves can be scheme dependent, right? It's not necessary for them to be scheme independent.
Yes, Wilson coefficient at the intermediate stage can be scheme dependent. But
so what are the terms that you want to be scheme independent? That's what I want to ask.
The observable should be scheme independent.
Correct. So that's all you're implementing, right? Not the intermediate terms.
Yes. So the final thing that you are going to measure at the experiment.
Great. Yeah. Thanks. That's clear. Yeah. Please proceed.
So, but scheme independence, as I said, can come from various things. So here, basically, the scheme dependence comes from some special, very special thing. Basically comes from a field eventually. So when you are computing the dimensional aberration loops, you deviate from the 4 dimensions. Okay. So if you are using the field transformations, those are not valid inside the Dirac setting. So because of that, you get some scheme dependence and you have to make sure the cancellation of that. Okay, so we don't have time for all this. Okay, so then here, in the EFTs, apart from the perturbative corrections that I talked about, all the loops, power corrections are also important because after all, this is a series in the which is suppressed by problems of lambda. So in some cases, the dimension 8 operators can also be important. So in this paper, we basically computed the full matching of dimension 8 corrections onto the big vector. So this is process dependent. You have to find which process is relevant, this is not relevant. So but we just presented the full calculation and then people can use it and see wherever they are relevant.
Sorry, quickly. So are there some dimension 8 which are relevant in terms of observables and what they can be?
Yeah. So one very quick example is that in weak effective field theory, there are some operators which do not match to the SMEFT dimension system. So they're matching to SMEFT dimension system 0.
Okay.
So they only match at dimension 8. Okay. So these are these 10 operators, and they only match at dimension 8 level. So any of these operators interferes in some operators will only get dimension 8 contribution. So,
but in experiment, are they relevant? Are we able to?
They are very relevant, yes. So these are basically dimension 6 operators.
Oh, I see.
So these are exactly similar to other operators, but their structure is different. So basically, if you count their hypercharge, if you put the hypercharge for various fields and sum them, that will not be 0. So these are hypercharge violating operators.
Yeah, I'm not understanding. So maybe we'll talk later. Yeah.
Yes. So basically, you can think of like this. At dimension 6 in SMAP, these are don't get any match. Okay, the 0 match. Only at dimension 8 level. So that's one example where dimension 8 matching could be important. But we did the full matching. Yeah. So this is a slide where different components of people. This is a development, basically summary of various developments that took place from 2013 to 23. So various components are computed by various groups. Group running by mostly this Manohar San Diego group, and we also did some parts. So I don't have any time for this. So this is basically application of this part is basically application of SMEFT. So Okay, so I will maybe talk about only this slide, not give the details. So here, basically, I want to say that the phenomenology in SMAPT is very interesting and rich and complicated. Exactly because of that, this is above the electronic scale, and the power interactions are also active. Okay, so renormalization group running can result into all the flavor changing branch. So that's how this makes it very interesting. Also, there are some non-standard artifacts, which is more complicated. We cannot talk about it now. So here I give some examples where UPAVAS can change the two operator UPAVAS can generate two operator. This will two the can be. So these kind of things can happen through the UPAVAS track. Sorry,
What is this I?
This one?
Yeah.
Oh, that's just ida tau to 5 star. That is conjugate. Okay, so I discussed various features which can the various phenomenological implications of all this renormalization group running, and finally we have so this is the whole procedure. So you will match your model to SNEFT and run from lambda to lambda scale, match at the lambda scale and run it down to do the scale. So this is the full chain of this technology. So for that we have developed some tools. So this is called Wilson. So this can do automatically the running and matching of within the snap and other entities. So this is basically the input is basically all the calculations done by various tools. Okay. Please let me know.